Welcome to Math with Professor V. In this video, I'm going to work through two examples where we're going to sketch the graph of a function using the process outlined for a typical Calc 1 student. So where you're going to find the domain, the intercepts, asymptotes, critical values, increasing, decreasing, concavity, all that good stuff. This was requested by my students in Calc 1 right now. I'm doing two pretty spicy problems from their practice exam that have to do with radical functions. So if you need a little bit more of an introductory lesson or you need some more basic examples of curve sketching to get you warmed up for this level, I have so many videos. They're linked in the description, so just go there first. But otherwise, I'm just going to jump right in. So first one we have is y equals x to the 1/3 times x squared minus 63. You can leave it as y equals. I just like introducing function notation. So I'm going to call this f of x is x to the 1/3 times x squared minus 63. The first thing we need to do is identify the domain of our function. Now notice here we have x to the 1/3. That's the same as cube root of x. And anytime the index is odd, then there's no restrictions on the radicand, aka the stuff underneath the radical. It can be negative, it can be positive. You're good. And then x squared minus 63, no restrictions there. So my domain's just all real numbers. How relaxing for us. Okay, next thing we need to do is find intercepts. Lucky for us, this thing's factored already. So x-intercepts, I set f of x equal to 0. So I would get 0 equals x to the 1/3 times x squared minus 63. Just use the zero product property. This tells me x to the 1/3 is 0, or x squared minus 63 is 0. So first one just gives me x is 0, or x squared is 63. Taking the square root of both sides, I get x is plus or minus rad 63, which is 3 rad 7. Okay, so for my intercepts, I'm going to list them as ordered pairs. This one over here, x is 0, and the y value is 0 on these x-intercepts. And then I also have plus or minus 3 rad 7, comma 0. And then just in case you want to know approximately as a decimal, that's plus or minus 7.9, comma 0. So that when we go graph everything at the end, you'll kind of know where to place them. Okay, beautiful. As I've mentioned in another video, when you have 0, 0 as an intercept, an x-intercept, that's also your one and only y-intercept. You can't have more than one y-intercept because then the graph would fail to be that of a function. So we're done. We have no more intercepts to find. All right, beautiful. Now let's see, do we have any asymptotes? Well, there's no vertical asymptotes because notice here, I don't have any denominators going on, right? And no natural log in here, nothing else that would cause a vertical asymptote to appear. Do I have perhaps horizontal asymptotes? Well, the way you check is you take the limit as x goes to infinity and negative infinity. So here's the thing to remember. Vertical asymptotes come from domain restrictions, right? The domain is all real numbers, so we're not going to have any vertical asymptotes. Another word when you talk about horizontal asymptotes when you're studying them is the end behavior of a graph. So when you hear that word end behavior, you should think limit to infinity. So let's take the limit as x goes to positive infinity of our function f of x. It's x to the 1/3 times x squared minus 63. Okay, and if you're looking here, what's going on? Well, x to the 1/3, as x approaches infinity, that's going to infinity. X squared minus 63, that's also going to infinity. Minus 63 does very little. And infinity times infinity, everything's just going to positive infinity. So that means the graph is going up, 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 up. Doesn't look like there's a horizontal asymptote. No. If there was, this limit would be some constant, a finite number. Now let's check. As x goes to negative infinity, on the other side, we have x to the 1/3 times x squared minus 63. Well, this time x to the 1/3, that's going to go to negative infinity, right? Because we're taking an odd root. That's the cube root. X squared minus 63, because of the squared, that's going to positive infinity. So I have negative infinity times positive infinity. Where's all that heading? To negative infinity. So again, on the left side, the graph is going down that way. So what does this tell me? There's no horizontal asymptotes. Okay, but you should just always check with a limit. All right, very good. From here, now we're ready to go ahead, take our derivatives, get our critical values, and do all that good stuff. Now, I'm going to remind you, f of x was equal to x to the 1/3 times x squared minus 63. Don't take the derivative just yet, because you would have to do the product rule. So instead, what you should do is distribute that x to the 1/3 through. Then I have f of x is, be careful now, so I'm going to add these exponents. 2 is 6/3 plus 1/3, this is x to the 7/3, minus 63x to the 1/3. Fabulous. Let's work with this. This is what we're going to work with to obtain our derivative. So f prime of x is going to be, bring that exponent down in the front, then subtract 1, so it'll be x to the 4/3 now, minus 63 times 1/3, that's 21. The new exponent is going to be negative 2/3. How are we doing? Okay, great. Now we need to clean this up so we can obtain critical values. When I see a negative exponent, I encourage you put it in the denominator. That's going to be just the simplest way to clean it up. You can try to factor when it's written this way, but it's very tricky for students to factor with negative exponents. So I'm not going to encourage you to go that route. Let's take the path of least resistance. So we have here 7x to the 4/3 over 3 minus 21 over x to the 2/3. How are we doing? Okay, now what would my common denominator be? Look at these two terms. Just 3x to the 2/3, right? Very good. So I'm going to multiply this first term by x to the 2/3, top and bottom, and then the second one by 3. So now let's see what we've got going on. So f prime of x is going to be, remember, we add these exponents together when multiplying. So 4/3 plus 2/3, that's 6/3, better known as 2. Yes, so this is 7x squared minus 21 times 3 is 63 over x to the 2/3. Wow, wow, wow. What a beautiful f prime of x we have here. All right, now let's go through. Let's get our critical values. Critical values come from two places. First place is where f prime of x is equal to 0. So that happens when the numerator of your derivative equals 0. So that happens when 7x squared minus 63 is 0. Okay, that means 7x squared is 63, x squared is 9, so plus or minus 3. Are those critical values? Are they in the domain? Yes, my domain is all real numbers, so we're good. Other place we get critical values is where the derivative does not exist. That happens when the denominator is 0. Let me fully color code this situation for you. There we go. So that would mean x to the 2/3 is 0, and that happens just when x is 0. And that's also within the domain. So those are my three critical values, plus or minus 3 and 0. Now I want to figure out intervals of increase and decrease and any local extrema. So let's use the first derivative test. I'm going to make a number line. Here's f prime of x, -3, 0, 3. Okay, good. Let's pick somebody over here and pick something nice. I know if I take a number and I raise it to the 2/3, it's always going to be positive. Why do I say that? When you raise something to the 2/3, that's the same as taking the cube root and then squaring it. Okay, so it's always positive over there. The denominator is always going to be positive. I can just plug in numbers now to the numerator to see. -4, let's do that one. So 7 times -4 squared, that's 7 times 16. That's going to be bigger than 63, so that's positive. That means my function f of x is increasing. Now pick something between -3 and 0. How about -1? 7 times -1 squared, that's 7 minus 63 is negative. Again, the denominator is always positive, so the derivative is negative from -3 to 0. Let's pick something between 0 and 3. How about +1? 7 times 1 minus 63, the numerator is negative. Denominator is always positive, so it's still negative on this interval. And then pick something bigger than 3. Then you can see this is going to be bigger than 63, so now derivative's positive, function is increasing. Okay, very good. So now let's see, where is f of x increasing? Let's list the intervals. From -∞ to -3, union 3 to infinity. Where is f of x decreasing? Make sure you do this carefully. From -3 to 0, union 0 to 3. You have to skip over 0 because the derivative is undefined there, okay? Do we have any local extrema? Well, look here. Right at -3, the function switched from increasing to decreasing. So that means at -3, we have a local max. And when you draw the arrows the way I have, it should look like a little max, doesn't it? Boom, boom, there's a max. And then right here at +3, notice the function switched from decreasing to increasing. So here's a lovely local min. Okay, so let's report that as well. We have a local max at x equals -3, -3 comma, and then I plugged it into the function for you. It's 54 cube root of 3. And then we have a local min at x equals +3, and it's at 3 comma -54 cube root of 3. Okay, good. If you need help figuring that out here, I'll do one of them for you. Remember, f of x was x to the 1/3 times x squared minus 63. If we do f of -3, this is x to the 1/3. That's basically, think of it like cube root, okay, of -3 times -3 squared. That's 9 minus 63. Okay, 9 minus 63, that's going to be your -54. And then I can break up this cube root of -3 into cube root of -1, cube root of 3. And then cube root of -1 times -54, cube root of -1 is just -1. So that's how I get that +54, okay? And then you still have cube root of 3. And then the other one is very similar. Okay, good? You're all right? Okay, now that's all squared away. We need one more derivative. We need a second derivative. Now be careful, because you can make this difficult or you can make this easy on yourself. So you have to choose carefully. Pick the nicest version of f prime to use in order to compute f double prime. What do I mean? I don't like this guy. This guy was so helpful for our critical values, but if I try to differentiate once again, I'm going to have to do the quotient rule. How nasty, nasty. Use this version of f prime right here. Oh, we can just go term by term and get f double prime. It'll make life so much nicer. So here we go. I'm just going to copy them down here. All right, here's f prime. We don't need this highlighted. And now let's get the second derivative, f double prime of x, all right? So same idea, bring that exponent down in the front. So we have 7/3 times 4/3, subtract 1, x to the 1/3. And then I have minus 21 times negative 2/3 times x to the negative 5/3. How are we doing? Good. Now we just have to clean up. Okay, so similar to last time, let's just put all the negative exponents in the denominator and we'll go from there. This is going to give me 28 over 9. So I'll put 28 x to the 1/3, 9 in the denominator. Now this is going to be positive 42 over 3x to the 5/3. So this time my common denominator is 9x to the 5/3. So the first term needs an x to the 5/3. And then the second term just needs a 3. So that's pretty good for us. So let's see here. F double prime of x is going to be 28. I'm adding those exponents. So 1/3 plus 5/3, that's 6/3, aka 2x squared, plus 42 times 3, that's 126, over 9x to the 5/3. Beautiful. Wow, there's my second derivative. Let's box it. That was pretty painless, I'm telling you. Okay, possible inflection points. Possible inflection points are very similar to critical values. They just apply to the second derivative and for inflection points. So they come from where the second derivative equals 0 or where the second derivative does not exist. Second derivative would be 0 if the numerator was 0. 28x squared plus 126. But let's stop and think about that. Can that be 0? No, right? That would mean 28x squared is a negative number. That's not going to be possible. So that doesn't give me any possible inflection points. Then other place I'm going to look is where f double prime doesn't exist. That happens when the denominator is 0. So that would mean 9x to the 5/3 is 0. That happens if x is 0, and that's in the domain. So that's a possible inflection point. But I need to check, is it indeed an inflection point or is it just a possible one? How do you check? Similar to the first derivative test, you make a number line. Here's f double prime of x. I'm going to put 0 on there and test on either side. Now remember, we said the numerator had no zeros. In fact, it's always positive, because if I square something and add 126, man alive, that's always positive. So just check in the denominator. Say you put -1. -1 raised to the 5/3, these are both odd, right? So you're taking a cube root and then raising it to the 5th, it's going to stay negative. So if I plug in a negative number, second derivative is going to be negative. That means my graph is concave down there. And then if I pick a positive number, say 1, a million, whatever, it's going to be positive. So positive over positive, second derivative is positive, which means my graph is concave up right there. Okay? So we have everything we need. I can list my intervals of concavity now. So the graph is concave up from 0 to infinity. It's concave down from -infinity to 0. And we do have an inflection point since there was a change in concavity. Inflection point at 0, 0. Okay, very good. So now let's plot everything that we found earlier. Besides the inflection point 0, 0, we had, remember we had intercepts, we had x-intercepts, and then we also had some local extrema. So let me remind you what all of that was, okay? So we had intercepts at plus or minus 3 rad 7, comma 0, which is about plus or minus 7.9, comma 0. And then we had a local min at 3, comma negative 54 times the cube root of 3. And you might be saying, Professor V, I can't graph that. I know, 1 second. So cube root of 3 times 54, 77.9. So let's say that's 3 comma negative 77.9. And then local max was negative 3, and then it'll be positive 77.9 approximately. So don't freak out. We're just gonna scale in a way that makes sense for us, okay? It's our graph. Here we go. I know I have to go all the way to like 77 in the y direction and negative 77. So let's say this is 50 and this is 100, okay? Negative 50, negative 100. Just, gonna have a relaxing time about it. Now you don't need to scale the x-axis similarly. X only needs to go up to about 8 and negative 8. So I'm gonna go ahead and do that. So let's say this is 4, 8. Let me actually scoot it over. Maybe let's have a little extra space here. I'll say this is 4, this is 8, negative 4, negative 8. There we go. There's negative 3. Remember, those are important. Here's 3. Blah, blah, blah. Okay, 4, 5, 6, 7, 5, 6, 7. Something like that. There we go. Very good. Okay, so let me put in first, we have inflection point at 0, 0. Let's put those intercepts in. 7.90, negative 7.90. Don't forget, this is an inflection point. Local min, 3, negative 77.9. Let's say that's about there. Local max, negative 3, 77.9, somewhere around there. Okay, now this is where you're actually going to use the concavity to help you. So look over here. This is our local max, right? The graph is concave down this entire side over here. To the left of the y-axis, the graph is concave down, and that's a max. So draw something that looks concave down where that's the max. Shouldn't be too crazy to do. Make sure you don't go any higher than that, and then turn back around. And remember, we took that limit as x went to negative infinity, and it went to negative infinity. So there you go. And then similarly over here, so there's a change in concavity. Now the graph's concave up, and this is a min. So just don't go any lower. Turn back around, cross through the x-axis right there, and it goes up forever. Okay. Now, obviously, we're just kind of narrowing in on this window here where all the action is going on, the local extrema, the inflection points. If you were to graph it and open up the window, this would just be a small little blip, and then the rest of the graph really just goes up and down forever, kind of looking like x cubed almost, all right? If you want to graph it using some technology, you can see what it'll look like, and that's always exciting. Okay, that ends that problem. How are you doing? Good. I have one more from the practice test that I promised I would solve. So example number 2. And this one is y equals x times the square root of 7 minus x squared. Okay, again, I like, rewriting it and calling them f of x. You don't have to, but it's just good to use function notation whenever possible, okay? So first, let's identify what's the domain here. We do have to be careful because I have a radical, even index, right? It's a square root. I can't take the square root of negative quantities. So 7 minus x squared needs to be greater than or equal to 0. Couple ways you can solve this. I think the easiest is if you just imagine the graph of 7 minus x squared. Yes, it's a parabola that opens downward, and it got shifted up 7 units, and it would hit the x-axis at rad 7 and negative rad 7. Yes? This is 7 minus x squared. And basically, I need to restrict my x values to where the parabola is above the x-axis, greater than or equal to 0. So hopefully you could see, well, the domain is going to be between negative radical 7 and positive radical 7. Good? That's it. So we have a restricted domain. Now let's go ahead. Let's find our intercepts. All right. So x-intercepts, I'm going to set f of x equal to 0. And I have x times rad 7 minus x squared. I'm going to use the zero product property. So either x is 0 or rad 7 minus x squared is 0. X is 0, that one's done. This means 7 minus x squared is 0. X squared is 7. So plus or minus rad 7. And again, see how 0, 0 is an intercept? So I also have my y-intercept. And then plus or minus rad 7 comma 0. So I have 3 intercepts total. Good? Now let's think about this. Vertical asymptotes. Vertical asymptotes come from where there's domain restrictions in the denominator. That's not going to happen here. So let's just tell everyone we thought about it. Not that we were careless, right? No vertical asymptotes. Horizontal asymptotes come from looking at the end behavior of a function, taking the limit as x goes to infinity and negative infinity. I can't do that here though, because my domain is restricted. It's bounded. I can't talk about what the function's doing as x goes to infinity because it's outside the domain of the function. So there is no end behavior for this graph. There's no horizontal asymptote either. And that's it, okay? Done. So then now we're gonna go ahead, we're gonna take the derivative. That came up quicker than probably expected, huh? So let me remind you, f of x here is x times the square root of 7 minus x squared. We need to use the product rule. Yes, very good. So f prime of x, first let's take the derivative of x. That's just going to be 1. Then you leave the other function alone, rad 7 minus x squared, plus now I'm going to leave x alone and multiply by the derivative of rad 7 minus x squared. So I've taught my class the shortcut. This helps them a lot of the time. When you take derivative of a radical function and it's a composition of functions, there's another function sitting inside. Here's the shortcut. You put 2 and the original radical in the denominator. And then in the numerator, you put the derivative of what's inside. You're doing the chain rule. So you have a negative 2x up here. Okay, good. If you've never seen that shortcut before, I'll link a video here where I walk you through it. Then these 2's cancel. This is good. So then now I have rad 7 minus x squared minus x squared over rad 7 minus x squared. And then just like last time, the best thing to do is get a common denominator, which is rad 7 minus x squared. So I'm going to multiply the first term by precisely that. And then remember, when you have a radical times the exact same radical, they cancel out. So you're just going to be left with 7 minus x squared up top minus another x squared over rad 7 minus x squared. Okay, almost there, guys. Hang in there. So f prime of x is 7 minus 2x squared over rad 7 minus x squared. Voila. Good, good, good. Okay, so now let's go get our critical values. They come from 2 places. They come from where f prime of x is 0. And that happens when the numerator is 0. So that would happen if 7 minus 2x squared is 0. So that would mean 2x squared equals 7. X squared is 7 halves. So x would be plus or minus rad 7 over 2. If we rationalize, that's plus or minus rad 14 over 2. Okay. Other place we get critical values is where f prime of x does not exist. That happens when the denominator is 0. That would mean 7 minus x squared is 0. So x, we can just say x is plus or minus rad 7. Those are in the domain, but they're on the edge of the domain, so that's fine. Also, it's helpful not to think of the rationalized form here, just to make sure that these are within the domain. Because I know we're bounded between negative rad 7 and rad 7. If I know that, oh, this was really just rad 7 halves, then I'm within the domain. It's easier a little bit for your mind to compute that. So here's 1, 2, 3, 4 critical values. Now I'm going to put them on the number line, but be careful because our domain is bounded. I'm not going to put arrows on this number line, and I'm not going to test outside of it. So negative rad 7 and rad 7 are the endpoints of the domain. So we're not even going to go outside of that. And then here we have, I'm going to leave it the unrationalized form. It's easier. Negative rad 7 halves and then positive rad 7 halves. Okay, good. So here we go. We're going to test all of these in the first derivative. Now don't get freaked out. You should know 7 halves is 3.5, right? So can you think of a number between negative square root of 3.5 and negative square root of 7 that you would like to test? How about negative 2? Because negative square root of 4 is over here, right? Yes. So negative 2. The denominator is always positive because you have radical, blah, blah, blah. So this is positive always. Now we said we were testing negative 2. Negative 2 squared, that's going to be 4. 2 times 4 is 8. I already did the next step in my head. So 7 minus 8, that's going to be negative in the numerator. So negative f prime, which means the function's decreasing. Okay, there's a lovely number between here, 0. So plugging in 0 for x, first derivative is going to be positive, increasing. And then between 7 halves and 7, again, you can just plug in 2 right there. Square root of 4 lies between those numbers. And again, this is going to be negative now, which means my function's decreasing. Okay, so let's go ahead and list the intervals of increase and decrease. The function is increasing from negative rad 7 halves to rad 7 halves. If you want to rationalize the denominator, if that bothers you, negative rad 14 over 2 to rad 14 over 2. But like I was saying, it was helpful to leave it unrationalized just so you can kind of reference the numbers more easily. Decreasing from negative rad 7 to negative rad 7 halves, union rad 7 halves to rad 7. And then, do we have any local extrema? Yes, we do. We have a local min right here at negative rad 7 halves. So I'll just write negative rad 7 halves, and then the y value ends up being negative 7 halves. And then local max, can you spot it? Yes, it's right here. So local max is at rad 7 halves, and then the y value is 7 halves. Okay, good. That's all done. Now we need the second derivative. And I'm sorry, but in this case, we can't play around with things. We just have to do the quotient rule. Okay, so f prime of x is 7 minus 2x squared over rad 7 minus x squared. Here we go. I always sing the song. If you're not familiar, I'll link a video where I explain it. F double prime of x. So low d high minus high d low, square the bottom, away you go. That's the quotient rule. Low means you write the denominator. D high means you multiply by the derivative of the numerator, that's negative 4x, minus high, so that's the numerator because it's high over low. D low means multiply by the derivative of the denominator. I'm going to use that shortcut again for radicals. So you have 2 with the original radical in the denominator, and then derivative of the radicand, the stuff underneath the radical in the top. Over low, low, or square the bottom, away you go. Okay, good. Let's clean up a wee bit. These 2's cancel. Also, these negatives cancel, okay? So I can write this now as rad 7 minus x squared times negative 4x plus 7 minus 2x squared times x over rad 7 minus x squared all over 7 minus x squared. And then hopefully I wrote it in a way where you can kind of see what we need to do next. We have a complex fraction because we have an extra denominator in the numerator. Oh no, that has got to go. So multiply everybody by what you're trying to get rid of, rad 7 minus x squared. And I have to do that in the top and bottom. Okay. And then we should be ready. We should be ready. So I'm going to distribute this now. Here and here. There's two terms. When I multiply this radical 7 minus x squared times the other radical 7 minus x squared, I'm just going to get regular old 7 minus x squared left. Negative 4x is minding its business. Plus, now when it distributes here, it just cancels completely. Boom, boom. So then I just have 7 minus 2x squared times x. Good? In the denominator, you have 7 minus x squared to the 3/2 power, because this first factor is to the first, the other one's to the 1/2, add them up. Okay, things are looking better. The worst is over, I promise you. Now we just distribute our little hearts out and combine like terms. So this is going to be negative 28x plus 4x cubed plus 7x, I'm going here, minus 2x cubed over 7 minus x squared to the 3/2. Okay, and then this ends up being dun, 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 f double prime of x 2x cubed minus 21x over 7 minus x squared to the 3/2. Whew, we made it. Okay, now let's see if we can find our possible inflection points. Possible IPs. I love a good abbreviation in math, so. First place we look is where f double prime of x is 0. So that would mean 2x cubed minus 21x is 0. Let's just factor. I can take an x out, and then I have 2x squared minus 21 is 0. Okay, so either x is 0 or x squared equals 21 over 2. But 21 over 2, that's bigger than 7. So if you get x's plus or minus rad 21 over 2, those are not in the domain. No. So cross them out. They are not possible inflection points. They're out of bounds. Remember, our domain is bounded. Okay, that's done. Other place that we get possible inflection points is where the second derivative does not exist. That would mean the denominator is 0. It doesn't matter what exponent is there. You just set the inside equal to 0, which means x would be plus or minus rad 7. Those are the endpoints of my domain, so they're not going to be inflection points. It has to be in the middle where there's a change in concavity. So we'll just test on the number line. Remember, it's bounded. Don't put arrows. So here's negative rad 7. Here's rad 7. This is f double prime of x. And here's 0 right here. Okay? Now, plugging in something, let's pick something nice, like negative 1. 7 minus negative 1 squared. This is positive. It'll all be positive down there. What did I say? Negative 1? Okay. So negative 1 cubed is going to stay negative. So this is negative 2 plus 21. Okay, that's positive then. So the graph's concave up there. Now let's pick over here something relaxing. How about positive 1? This is positive. 2 times 1, 1. 2, excuse me. 2 times 1 is 2. Minus positive 21. So then 2 minus 21, that's negative. Concave down. Ooh, so we've got an inflection point. Inflection point at 0, 0. And then the graph is concave up from negative rad 7 to 0, always parentheses, and concave down from rad 7, or from 0 to rad 7. Okay. All right, are you ready to put the graph together? We have this. We had some local extrema. Did you forget? Probably. Let me remind you. Local min, negative rad 7 halves, negative 7 halves, and then local max, rad 7 halves, 7 halves. And then we also had intercepts besides 0, 0, plus or minus rad 7, comma 0. Okay, so you have to include all of that on the graph. Very good. If you want to know as a decimal, okay, rad 7 halves is about 1.87, so let's say 1.9. Okay, so approximately negative 1.9, negative 3.5, and then this is going to be positive 1.9, positive 3.5. Okay, very good. Square root of 7 also is about 2.6, plus or minus 2.6, comma 0. If you're in my class though, you know, and I don't give you a calculator, you're just going to label your number line and say this is rad 7. We don't really stress outside of that. Okay, let me use the page break as my x-axis. Here's y. Thank you for giving me an x-axis already. Okay. Here we go. We don't have to go too crazy, huh? 1, 2, 3, 4, negative 1, 2, 3, 4. And then in the x direction, I'll do about the same. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Inflection point 0, 0. Let's put the local mins and maxes. So negative 1.9. Negative 3.5, here's my local min. Local max 1.9, positive 3.5, so right about there, max. And then the intercepts, those are very important. So plus or minus 2.6. And remember, these are the endpoints of the graph because the domain is restricted. So don't put arrows. This is like literally where the graph ends. Okay, from here you should be golden. 0, 0 is an inflection point. Okay, we can tell the people that also. And then look, the graph was concave up on the left of 0. So it's concave up here. Make sure that's your min. So just draw something concave up. Don't go lower than the min. Turn right back around. Okay, and then now the graph is concave down over here. That's your max. So just don't go any higher. This way, and stop. No arrows, please, right? Domain is restricted. And that's it. That concludes the problem. I think the trickiest thing with this one was getting that second derivative cleaned up and ready, and maybe the numbers are a wee bit ugly. That is true. Most likely, if I put this on the test, I would change it so you had like something that was a perfect square and you didn't have to deal with rad 7s. Got it? Okay, that concludes the video. Hopefully you hung in there. If you did, you are magnificent. And please leave me a comment letting me know. Say, I am magnificent. I made it to the end. Give the video a thumbs up. Subscribe if you haven't already. And if you need more help with Calc 1, 2, 3, I have full video lectures organized into playlists. And also please follow me on Instagram, TikTok, Math with Professor V. I love you all. I'll be back sooner than later. Bye.